Hi, good morning to the Evaluation Committee. My name is Dan Marom, and I will be describing a little bit my activity and my work here at the Hebrew University at the Institute of Applied Physics. So I joined here around at 2005 following a PhD that I had acquired in the US at UC San Diego. Following that, I worked for 5 years at Bell Labs, Lucent Technologies at the time, where I worked on photonic devices, specifically with a focus on wavelength selective switches. In 2004, I actually got a position here, but I only joined eventually in 2005 and made the transition from the US here to Israel. And I was actually the first recruit of the then Applied Physics department, following a very long hiatus in hiring due to various reasons. At the time, the Hebrew University opened the engineering school called the Computer Science and Engineering School. As mentioned, I was the first hire in the Applied Physics department, and I joined a small department at the time, the most junior faculty amongst a faculty which is much older. And following, I guess, my hiring, the department continued to hire and expand, and we've seen tremendous growth since that time. And I've had the privilege, of course, of starting my lab, which I'll describe a little bit later. But in addition, I've also chaired the department for 5 years, which were a bit tumultuous just because during that time we had left the School of Engineering due to some differences in the role of the Applied Physics department, and we at that time became an independent department within the Faculty of Science, and then our hiring had continued since, and now we have transformed from being a department into an institute, which I'm sure Yossi, the Institute Chair, has spoken at length about. So I joined again in 2005, and I opened my lab, which I call the Photonic Devices Group, or Photonic Devices Lab, which has an acronym PDL, if you know what that is. During that time, we had pursued various projects related to photonic devices, with particular emphasis, I guess, on devices that are relevant for optical communication, so optical fiber communications. And during that time, of course, besides training numerous PhD and master's students, we had focused on making devices, both what we call linear and nonlinear devices, making use of both free space and much more focused now on guided wave solutions. And we're using various platforms such as silicon nitride, and again, free space optics. We're also now using new tools available to us, such as three-dimensional printing at the nanoscale, which allows us to fabricate photonic structures which control light propagation, and again, by creating structures which are both nano or sub-wavelength and more macro or bulk optics, but again on a very small scale. And again, together with fiber optics, so we use conventional fibers in the past, and since I guess 2010, with the advent of space division multiplexing, we're using more and more specialty fibers. So these can be both multimode fibers as well as multi-core fibers. So we're using those platforms to realize, I guess, innovative devices that we think can be of use for future optical communication networks, also for data centers. And then we look at ways how we can efficiently switch, filter, manipulate light that's coming from these fibers in order to achieve required functionality. Some of the specialty fiber at our disposal, or one particular platform we're advancing, is a unique fiber that's been made for us at Corning, which is a rectangular core fiber. So this is a fiber idea that we had devised of having a core which is designed to be single mode in one dimension and multi-mode in the other dimension. And that has huge benefits as far as both propagation, but also in device integration. And we're doing various devices using that fiber in order to demonstrate the ability of using this fiber in what we call MIMO-less, or without incurring mode mixing in the whole transmission link. So again, we focus on devices, but I have to mention that we're not really a system lab, so we don't have the capability of doing high-speed testing, like generating and detecting high-speed communication signals. For that, we rely mostly on collaborations. So we have a lot of joint activities with both research labs around the world, as well as industrial companies. And we typically collaborate in various funding schemes that create collaborations, such as the European Union, European Commission programs. And for instance, we have currently two programs running. One is called FlexScale, the other is called Proteus 6G. Both of them focus on communications for the upcoming sixth generation of cellular networks and looking at the backbone requirements for transmitting all the information there. And we have devised novel ideas in order to, again, control the data flows and increase the capacity and availability. We also collaborate in national programs. So we have three such programs, one on silicon photonics, the other on quantum communication, and the last on VCSELs. And for example, in the VCSELs project, we're looking at efficiently multiplexing multiple VCSELs, large arrays, into a fiber in order to have efficient power delivery. We have, of course, other different projects. I've mentioned a little bit the nanoscribe, or the printer that we print at the nanoscale, and we specialize specifically on printing on an optical fiber tip. We've demonstrated various functionalities. I'll just mention maybe one here, of a sensor, which is basically a ring resonator on a fiber tip that's been completely 3D printed. And it's printed on a dual core fiber, so we can send light from the distal end of the fiber and get the reflected light or the returning light through the other core, so we get a very clean signal, and we can sense what's occurring at the distal end of the fiber. So these kinds of projects are all what we call the linear activities. We also have some activities in nonlinear optics and nonlinear signal processing using parametric processes. This has been a little bit downplayed in the last few years, but still we have that capability of looking at nonlinear phenomena in specialty waveguides that we've worked on in the past. But currently, again, the focus is more on devices and silicon photonics. One particular topic that we're trying to merge is, again, this ability to 3D print structures in the nanoscribe printer, and using that to facilitate efficient fiber coupling between fiber and chip. So we have an experimental lab, which I'll take you on a tour soon, and you'll see some activities taking place currently in the lab. We have a fully stocked lab, again, mostly devoted to test and measurement equipment in the telecom region. So we're focusing mostly around the 1550 band. Recently, we're expanding due to expanding interest in the wider communication band, which we call the SC+L, which roughly extends from 1460 to 1625 nanometers. So we have tunable lasers, wideband sources, optical spectrum analyzers, and optical vector analyzers, etc. And all the students work collaboratively on the various projects and demonstrate what we're trying to develop, and then assist in meeting the requirements of the optical communication field.
Good day, my name is Alexey Kukin. I am a researcher in the lab of Marom, and here is a setup for characterization of VCSELs that we use in the project for efficient power coupling from the VCSELs in the fiber. VCSELs placed on this position, and here is we collect light from VCSELs by objective. It's going through the splitter and going to the camera and to the spectrum analyzer, so we can get characteristic of power distribution in the beam and spectral characteristic of the VCSELs.
I'm Dan Scheffer. I'm a master's student at Marom's lab. My system is a free space optic system. We're trying to achieve a true time delay with components such as grating, optical light modulator, and LCOS. Using this true time delay, we are trying to achieve a phased array that will be used for various applications.
Hi, I'm David. I'm a master's degree student in the Marom lab. Here, this is my setup. I have a silicon photonics chip on a vacuum table. On the silicon chip, we have a high performance mode multiplexer. My main goal is to create a transmission system that includes a fiber array, a vacuum table with a chip. On the other side of the table, we have another fiber array and another chip with a demultiplexer this time. And in between, we're going to have a multi-mode rectangular core fiber. This technique is called space division multiplexing.
Hi, I'm Yoav Dana, PhD student in Marom's lab. So I'm working on space division multiplexers, especially photonic lantern multiplexers. We are fabricating it in the nanoscribe 3D nano printer and make these micro scale multiplexers. So besides of designing and fabricating, I'm actually characterizing it here in the setup. So we have this setup of digital holography that can resolve the eigenmodes and the complex field of the system. So this is how we characterize it. Recently we took one of our devices to Bell Labs in the United States to make system experiment with it, and this work should publish very soon.